All right, and we're back. Okay, let me... Oops. All right. Okay, so oxygen demand. We've been talking about it for a couple weeks now with wastewater treatment. And so today I want to flesh out a little more specifics about what exactly I'm talking about. And that way we can have a better context of, okay, how do we measure it? And how do we deal with it downstream when we encounter situations where we discharge some waste. We want to understand how much of an oxygen demand burden it's going to be on the stream or river or lake, whatever it is. So talked about it a little bit. Let me just begin here and say you could call it biochemical or biodegradable, biological oxygen demand. Essentially, we're saying the same thing. And this is some amount of oxygen that's going to be demanded over time. So typically, we'll end up giving it a BOD and a 5 as a subscript. We often give it 5 days. So you'll see BOD 5. That's just standard convention. It's the number of days in a work week. It's not a full week. It's enough time for the bacterial activity to get going and to process. Should not be limited by the amount of bacteria that's in there. Usually, sometimes we'll have to add some in the first place, but they'll be growing. They'll have plenty of time to grow and consume oxygen. And that's also a pretty typical time frame of if we discharge wastewater into a stream or river, the bulk of the oxygen demand, from a biological perspective, is demanded in about that amount of time. So it gives us a pretty good handle. 5 days is kind of a long time to discern, okay, how much waste is still in the wastewater. So it's, in that sense, it's not super ideal, but it works pretty well. And so we'll talk a little bit about potential alternates for that. So it's microbe food. Essentially what's going to happen, just like when we eat something, we're going to breathe in oxygen, consume those organics to make new cells and to make energy for the growth. And so that's going to be essentially oxygen consumed, CO2 emitted, and the consumption of the organics there. Now, we can take a look at the theoretical oxygen demand if we know exactly the kinds of chemicals we're dealing with. So if we knew that our wastewater was completely filled up with glucose, then we could calculate the absolute maximum oxygen demand that could be possible by saying, okay, well, let's say we have one glucose molecule, and do some stoichiometry here, and we're going to oxidize that with some amount of O2. The products here are going to be CO2. It's essentially a combustion reaction, right? But we're doing it typically with microbes, or the theoretical here is just saying, well, at most we're going to demand some amount of oxygen to get to oxidize this glucose. So in this case, we have C6H12O6. We'll get 6 carbon dioxides from that. Then we can balance the hydrogens. We've got 12 on the left, so we'll need 6 times 2 to get 12 on the right. Then we look at the oxygens. We have 12 here, another 6, so that's 18. We've got 6 here, so we just need another 12, be a 6 here. So for every 1 mole of glucose, the theoretical maximum amount of oxygen that can be demanded is 6 moles. Okay, and we can convert that to mass. If we have the molecular weights on hand, maybe it's for every pound of glucose, it's 10 pounds of oxygen or something, right? So that gives us a way to calculate the theoretical maximum, but in reality, there's a couple issues, right? We don't ever have that much information about what's in our wastewater, right? Maybe a sugar processing plant, right? Sugarcane plant or something would have, maybe that's applicable to an extent, but even still, it's nowhere near realistic to think that every single sugar molecule will be fully oxidized and all that will happen perfectly, right? Maybe the bacteria essentially oxidize 5 of the 6 carbons, and the other carbon becomes something else, and it doesn't end up demanding oxygen. Okay, so in reality, that's just a theoretical maximum, right? That's complete ideal combustion or something. So a intermediate step that can get us an answer much quicker would be a chemical oxygen demand technique. And so this is kind of an experiment. You could run it in an instrument, take maybe an hour, and get an answer for how much oxygen demanding substance is in your water given this chemical process. So you take it and subject your water to a chemical process that's going to essentially cause oxidation at all costs. So you're basically burning it. In water, that usually looks a little more like using high temperature. Maybe you're adding some oxidizer like sulfate or something that just has a lot of oxygen that really wants to react with stuff. Sometimes you'll add ultraviolet light, and essentially what you're going to do is oxidize it, and you're going to form CO2, water, and if there's nitrogen in the stuff, you'll probably form nitrogen as well. Okay, so that's similar to BOD, except in BOD you're forming new cells, you're getting probably some stable byproducts that have not oxidized all the way to, let's say, nitrogen gas, in terms of the nitrogen stuff. So they're comparable, but COD is always going to be, estimate a little bit more oxygen than BOD, because it's just a harsher chemical thing. So if we were to rank order these, we'd say theoretical is the theoretical max. Then we have the chemical. That's a quick and easy technique if you've got the instrument. You can blast it and measure. You'll probably be tracking, by the way, the CO2 coming off. There's a very similar technique called total organic carbon analyzer. That's going to essentially measure the organic matter in their total. It's not so much concerned about the oxygen demand, but it's quite related. Okay, then we'll have BOD as the last remaining one. So that's a little bit of context here. So if we're trying to do some environmental measurements, COD can be quite useful sometimes. And sometimes it can help us detect, let's say, if a landfill leachate collection system is failing, there's going to be all sorts of organic matter present, oxidizable from just leaching out of the landfill. You can often detect that quite well with just simply chemical oxygen demand. So that's a case where we would use it for an environmental purpose for detection, whereas usually for wastewater discharge that we know we're discharging it, we'll typically give it the BOD process to be sure that we're within the range that we think we are. So a little caveat here, we can subdivide the BOD into a couple types. First being carbonaceous, so basically some organic molecule that has carbon in it, that's what this is saying, is oxidized like we were talking about sugar, forms, we've gotten rid of that bond, take away the carbon, form some CO2 and all that, right? Likewise, we can take nitrogen, especially in the ammonia form, or maybe some amine form. You could take a organic molecule that has NH2 attached. That's basically the same. It's just attached to some other organic molecule instead of another H there. So either way, you can oxidize it and create, really it's nitrite first. This is not chemically balanced. If we went to nitrite first, NO2 minus, I guess that would be balanced. And then you'd add some more oxygen to get it to nitrate. But the overall process is you're oxidizing the nitrogen to nitrate ultimately, and perhaps even further you can denitrify it, which is, even though you're removing the oxygens, you're technically oxidizing the N. You can get to N2 gas eventually. Now that's a little different, and that's not quite an oxygen demand. That's just the final product of oxidation. So I'll just set that aside for now. But as you see, taking ammonia and getting it to NO3, you need 3 oxygens for that, right? You need 3 oxygen atoms to get from NH2 or NH3 into NO3. So this all relates to kind of the nitrogen cycle. In the atmosphere, we have tons and tons and tons of nitrogen gas. That's like 78% of our atmosphere, breathing that all the time. Plants can take that up to an extent, especially with the help of nitrogen-fixing bacteria. But typically, they're going to be taking organic or these nitrate, nitrite forms in from the roots. Then they're going to make this organic nitrogen. Right? These are their plant cells, bacteria cells that eat the plants, all of that, animals. We end up with all this organic, or at least bioassimilable, bioavailable is the right word, nitrogen forms. And once it's in that form, then it takes oxygen to move it back towards the other side of the cycle. So all that to say, if we discharge a bunch of organic matter that has a bunch of organic nitrogen, bacteria will use it just like they use carbon as an energy source because it's energetically favorable for it to go from ammonia, so NH3, to nitrite or nitrate. So they get a bit of energy from that, so they'll do that. So that's just another component of the oxygen demand that happens in reality. Okay, so little subdivision there. A bit of a side note. How do we measure the BOD? And here I went ahead and put in BOD 5. So first of all, it's going to be 5 days of microbe growth. And what we say is what we'll do is we'll take an airtight bottle, and it's quite typical to use 300 milliliters, just kind of a standard size. It's about that big, pretty easy to handle. It'll be airtight so that there's no oxygen exchange with the open atmosphere. It's going to be, we're going to prevent light. So you see in the past I've marked an X through this. We could use this bottle, but we just have to wrap it in aluminum foil. But bottles about that size are pretty typical, culture vials. Maybe these amber ones so you don't have to foil it. It's going to block all the light that could be used for photosynthesis, because photosynthesis would take the carbon dioxide that some process produced, and it would take CO2 plus that light and give us oxygen. So that's going to reverse the process that we're trying to measure. Right? So we're just going to set that aside and say, nope, let's not do that. Yes, that'll happen in nature to an extent, but we want to control what we want to measure is just the oxygen demand. Right? That's what we're interested in. We can do the other calculations on a natural system if we need to. And by the way, all the organisms that can photosynthesize can also do regular respiration, especially at night. So they're also going to be demanding oxygen. Even our plants will demand oxygen, even though they create more oxygen than they demand. Okay, so then we sit it there for 5 days, let the bacteria munch. We measure the dissolved oxygen before and after, and that's pretty much it. Sometimes we'll have to dilute these bottles because there's just not enough oxygen in them in the first place to support that amount of drop of oxygen from the biological activity. So if we have high strength wastewater, or even a medium strength wastewater, we can't just do straight up wastewater in here because it'll deplete the oxygen. Our little oxygen meter, maybe we started at 8 milligrams per liter. After a day or two, all that activity, it might be reading at like 0.5 milligrams per liter, but that's its detection limit. So we ran it all the way out of oxygen, and we have some measurement, but it's not a valid measurement. So we actually have to keep it within some range. So the wastewater is simply too strong for typical dissolved oxygen saturation. So if we were to test, let's say, some river or lake water for its BOD, we probably would have enough, right? Even if it's got a bit of organic material in it, maybe a really organic rich bayou, maybe not, or something, but usually it's fine. All right, so I'm going to we'll go through this slide, and then we'll stop there so that we get a kind of the initial impression of how we're going about calculating these before we'll save kind of a little bit more in-depth analysis for next time. So to measure BOD5, the calculations are pretty straightforward in the simple case. Let's say we have our bottle. We have some amount of, we've got it filled up to the top basically with our water, and we've got some amount of dissolved oxygen in it in the first place. So DOI meaning dissolved oxygen initial. That's going to be milligrams per liter of oxygen. We're going to take that and see how much is removed over the 5 days, right? So we have an initial and a final measurement. That's it, right? If we just had complete wastewater or whatever our sample water is, that'd be our answer. It demanded 5 milligrams per liter of oxygen. If we have a dilution, which is very, very common, we have a dilution factor. So if half of it was wastewater, then we'd take whatever, and we assume that there's nothing demanding oxygen in our, let's say this is our wastewater, let's say, and then we have some sort of dilution water, right? Should be pretty clean. We'll talk about what happens if we need to add some bacteria and stuff next time. But for this case, we have the wastewater and the dilution mixed together. I'm just showing them separate so you can kind of conceptualize it. And let's say that means, let's say this is 1/2 and this is 1/2, right? So then P is 1/2 because the P is just going to be the fraction of the total that is wastewater, right? Half of this is wastewater, so P is 1/2. You could say maybe that's 150 milliliters here. This is 150 milliliters here. And so when you calculate that, that's 150 divided by 300 is 1/2, right? So when you do P as 1/2, then let's say you measured 4 milligrams per liter oxygen drop over those 5 days, then you're going to have to double it or divide by 1/2, right? So that makes sense. You diluted your wastewater by half, you measured a value, so you multiply it by 2 because you had diluted it, right? It's very straightforward here. So we will get to a few small complications with the dilution process because a lot of times we have to add some bacteria to make sure, if we add a whole bunch of very clean water to just a tiny bit of wastewater, we might not have enough bacteria to survive. So we end up adding some bacteria, which means sometimes we add a little bit of BOD even with the dilution water. It just complicates it a little bit, but not too bad. So we'll go over some examples and we'll flesh that out a little more next time, and we'll pick up here. All right, so have a good weekend. I'll get the exams posted to Moodle soon, the grades that is.